Welcome back to my YouTube channel. Subscribers, if you're not a subscriber, please subscribe right now. So today we're going to be going over story sheet 13. Question 2. It's on simple amount of motion. And if to make video requests, for any questions, you can send the questions to 0978957975. You can send the video of the question, the picture of the question on WhatsApp, then I can make a video about it. So now, question 2, it reads, a 2-gram block connected to a light spring for which the force constant is 5.0 newtons is free to oscillate on a frictionless horizontal surface. The block is displaced 5.0 centimeters from the equilibrium and released from rest as in active figure 18.1. Find the period of its motion. So before you can even start answering the questions, we can do what we have to do essentially in any physics problem. The first thing is to gather the data. Others do the data after the free body diagram, others do the free body diagram before the data, and others do it with, put the data on the free body diagram. But let's start with the data. So I've been given the mass M, which is equal to 200 grams. So I think we can convert even from here. It's easy to convert. We can say this one divided by 1000 is 0.2 kg. That's converting to SI units. The second thing we're given is the force constant. So the spring constant. K is equal to 5.00 Newton per meter. This one is in SI units. Then we have got the displacement, which is 5 centimeters, which is typically the same as the amplitude. The amplitude is the maximum displacement. Amplitude. Okay. Others use x naught, but it's still the same thing, which is 5.00 centimeters. So divided by 100 to get a meter, we're going to have 0.05 meters. So then the first question says find the period of its motion. So the formula for the period T is equal to 2 pi square root of m over k. So we're going to have 2 pi square root. Our mass is 0.2. Then our constant is 5. So now we're going to now find this in our calculator. So 0.2 divided by 5 is equal to 0.04. Then the square root of this will give us 0.2. Then we'll multiply it by 2, then by 5, by 2, then by pi. Then start that again. 0.2 divided by 5, then the square root, then you multiply that by pi, then by 2. It's giving us 1.2566. So period is measured in seconds. So we have our period T is equal to 1.2566 seconds. So then we go to question B. We go to question B, which says determine the maximum speed of the wave. So we have our data, and I forgot to draw the free body diagram. Sorry. You can draw that maybe as your initial, then that as your final, then you can label this to be 0.05 meters. Then you can have this to be your mass. I think that's all with the horizontal surface as frictionless. So we've go to question. This was A, so we go to B. Go to B. So B is telling us to find the maximum speed of the block. So put that here, put that here, and put that here. So the maximum speed of the block. So we have got 2 ways. That's B. So the first way is we know since it's starting, since in the question it has it's starting at x is equal to 0. So we can use the cosine function. So I've got A cosine W t. That's according to sinusoidal motion. Then when you find the velocity, we're going to find the derivative of this, which is v is equal to we're going to have our f, since a is the constant. Then we're going to have the derivative of this, which will just be w. Then I've got the derivative of the inside function, which is negative sine wt. So we have our v being equal to negative a w sine wt. So now we're being told to find the maximum velocity, and this is the function, the formula for velocity with respect to time. So now what we're going to do here is you're going to notice that the sine function has got the range from -1 to 1. So these are the highest numbers that we expect to find in here. So the maximum velocity will occur at when whatever function is in here gives us 1. So we're going to have our v being equal to, when this is 1, AW, we can say -1. When this is -1, then it will give us v is equal to AW. This can also be equal to 1, but then it will give us the maximum velocity in the other direction. Remember, the negative is not implying that when you have the negative here, it does not imply that the velocity will be less than the other. It will be the same, only that it will have a different direction. So we're going to assume positive for here when we try this by that one. So this will give us the maximum velocity. You can even put V max there. So then we have not found our angular frequency yet, but then it's given by square root of k over m, because this squared is equal to k over m. So when you find the square root, it will give us this. So we can use this formula to find the angular frequency, which we are going to use here. So now w, this is omega by 1 of w, is equal to our k is 5 newtons. Then our mass is 0.2. So now omega is going to be equal to 5 divided by 0.2, 25. Then the square root of 25 is going to be equal to 5. 5, that's rads in second. Going to be pause. So now we can put that there, and then we've got our amplitude. We said our amplitude is 5 centimeters, which is 0.05 meters. So now B max is going to be equal to A, which is 0.05, B multiplied by 5, B max. So our B max is going to give us this one times that one. It's 0.25. That's meters per second. So now we have our B max, which is equal to 0.25 meters per second. So now this is the first method. We can also try the second method, which will still give us the same answer anyway. Let's just try it. Then in your solutions you can use any of the methods that's easier for you. So the first one is to say we know energy is given by the total energy of a spring. When you have a spring, sorry to take you back to inside the motion. So we have got that. We have got our A there. Then like this is x. This is like the x-axis. So the energy is given by the kinetic energy plus the potential energy. So now when it's here, it stops momentarily. So the kinetic energy is 0. But then here we're going to have our A being maximum. So we have got E. Let me say E is equal to 1/2 K. K is mv squared plus 1/2 kx squared. Potential energy, kinetic energy. So here the kinetic energy is 0. This is 0. But then A here, the x here is equal to A. So the energy at this point is 1/2 k A squared. Then the energy at this point, the x is 0, so like the potential energy is 0, but V is maximum. So E is equal to 1/2 mv max squared. So we have got, this is our equation 1, this is our equation 1, and our equation 2. So we can actually equate this one to this one, because we have got here we have got two unknowns, which is actually the energy and the V max, and then the K is known, the A is known, and the M is known. So we can equate the two. We are going to have 1/2 K A squared is going to be equal to 1/2 mv max squared. So now here what we are going to do is we are going to multiply the entire equation by 2 and then divide it by m, so that we can make V max a subject of the formula, and then later we are going to find the square root. So like these two will cancel with these two and these two, then the m will cancel with this m, then the m is going to come over here. So I'm going to have V max squared being equal to K over m A squared. Then when you get the square root, we're going to get V max being equal to A squared, the square root, and the square root of K over M. So the square root of A is equal to just A squared is A, then K over M, remember this is W. So this brings us back to the equation that we had, then when you find, you're going to find the other answer. So we can go to C, which is what's the acceleration of the block. So what is the acceleration of the block? So now, acceleration of the block. So let's see, sorry. So the acceleration of the block as well has got two ways. So the first one is, our equation was V is equal to negative A W sine WT. So when we differentiate this one, we're going to get the acceleration. So the derivative of the velocity is the acceleration. And the derivative of all this and this is a constant. So we're going to like, not count it. Then the derivative of sine is cos WT. Then you find the derivative of the inside function, which is simply W. So W times this W, are going to have our A being equal to negative A W squared cosine WT. So now remember, the max, this cosine, even if you put cosine 1 billion, even if you put cosine 1 trillion, even if you put cosine 0.001, it will always give you a number that ranges from negative 1 to 1. So these are the largest numbers from this direction and that direction that we can find here. So our maximum acceleration, our A max is going to occur at negative A W squared, and then in here when this one is negative 1. So I'm going to have A max being equal to A W squared. That's all. So then here what you're going to do is you're going to get your A M X is equal to our our amplitude was 5 centimeters, which is 0.05 meters. Then we have got our omega. Our omega was our angular frequency. It was angular frequency. We found 5 rads in the other question. So then this is squared. So our A max is equal to let's find. So I've got 5 to the power 2 times 0.05 to give us 1.25. So I've got 1.25 meters per second squared. So we found our acceleration. Then that's method 1. Then method 2, to get this formula, what you can do is, we know F is equal to M times A, and then we also know that F according to Hooke's law is negative Kx. So we can equate this equation. This is our equation 1, our equation 2. We can equate our equation 1 to our equation 2. We're going to have M A is equal to negative Kx. Then what we're going to do is we're going to make A the subject of the formula. So A is going to be equal to negative K over M X. So now remember, this K over M is there is this formula W squared. I keep saying W, sorry, omega squared is equal to K over X. Others know it as this one is equal to the square root of K over M, sorry. So like when you square root, when you get the square root of both sides, you're going to get this. So now this one is the same as negative W squared X. So now this X, the largest number that you can get for X is actually A, the amplitude. So we know that A is equal to negative W squared A. So now remember, when A is the other side, it will be negative A. When it's the other side, it will be positive A. So the maximum acceleration, you can just put the negative there and give us A is equal to W squared A. Which when you substitute will still give us the same answer, then we're going to get our A max being equal to, our A max was 1.25 meters per second squared. So that's that one, that's our C. So we finished our C. We're going to go now to D. Express the position, velocity and acceleration as functions of time in SI units. So I'm going to express the position first. So since this is sinusoidal motion, we have A, its X is equal to A cosine WT. So now when we find the derivative of this, we're going to get it as a function of time, the velocity as a function of time. So now when something says as a function of, what it simply means is what's on, this is the position, the X, then what's on the other side, they should all be constant apart from time. So this is the constant, this is the constant, then I've got our time. So it's as a function of time, which means as the time changes, the X will be changing, since the A and the angular frequency is actually not changing. So now we have got, we find the derivative of this. So V is equal to, what we're going to do is we're going to get this as a constant A, then we find the derivative of, typically we use the substitution rule, the one for cos WT, where we're going to let U equal to WT, then we're going to say W dy, this one is Y, so we're going to say Y over dx is going to be equal to dy over d, mu over du over, let me say dy over dt, sorry, dy over dt, then du over dt. So now dy over du, that's when we let this one equal to u, we're going to have y being equal to cosine u. So dy over du is just going to be simply negative sine u, and then du over dt, that's the derivative of this one. Since this one is a constant and this one is a variable, we're going to have this one simply being equal to w. So we're going to have our negative w sine, the u is just wt. So this is what brings us to this. In short, we just find the derivative of the trig function and then the derivative of what's inside. So I'm going to have negative sine wt times w. V is equal to a negative w sine wt. Then the derivative of this one will give us the acceleration. When you find the derivative of this one, it will be simply, it's just cos. Because what's inside still remains. Then outside I've got our w, then this one times that one, we're going to have our a being equal to negative a that squared cosine wt. So now this is the velocity as a function of time, then this is the displacement or simply the position as the function of time, then this is the acceleration as the function of time. The only thing that's going to remain is us to plug in the values. So here we're going to have our x is equal to a. A is just the amplitude, which was 0.05 cosine. Omega was 5t. Then for this one, we have our v is equal to our v is equal to aw. So it means this one times this one, which is 0.25 negative sine 5t. Then a is a, so that's this one. So that's like multiplying this one times that one again, which would be equal to 1.25. That's cosine 5t. Then that's how you express them as the function of t with putting the values. This is just like the general formula, but then when you plug in the values, you're going to get something like this.